Hi, our group researched the relationship between magnetic fields on current-carrying wires using the right-hand rule. The magnetic field was discovered in 1819 by a Danish scientist named Hans Christian Ørsted in a demonstration. In this demonstration, Ørsted was showing his class how to create a current through a wire with a battery. However, whenever he turned the battery on to create the current, he noticed that a magnetic compass near the setup was affected. He then made the realization that it was the current itself that was creating a magnetic field to affect the compass. It was also discovered later that not only does a current create a magnetic field, but also an external magnetic field can affect a current-carrying wire. This discovery allows the creation of modern technologies such as modern resonance imagery, or MRI. Technologies such as this have allowed for breakthroughs in detecting and diagnosing medical problems. This three-dimensional operation involving the magnetism and the current is modeled perfectly by the right-hand rule, which Trevor will elaborate on later.
Because physics has to be super confusing, a force that acts on a current does not always move the current in that direction. To keep this from giving you a massive headache from thinking about it, these right-hand rules can be used to model the relationships between the direction of current, direction of the magnetic field, and the direction of the resulting force. This is known as the right-hand rule. It is the gang sign for physicists. In order to do it, you take your pointer finger, and that's in the direction of the current. Your middle finger points in the direction of the magnetic field, and your resulting thumb points in the direction of the force acting on the current. There are two forms of this right-hand rule, and they model different relationships. The first form shown here is the right-hand rule that demonstrates how, if the direction of the magnetic field is known, as well as the direction of the moving charge, then the direction of the resulting magnetic force can be known. As was previously stated, if you point your pointer finger in the direction of the current and your middle finger in the direction of the magnetic field, then your thumb will point in the direction of the magnetic force acting on the current. Unfortunately, things have to get just a bit more complicated, because if you were dealing with the flow of electrons, then your thumb will point in the opposite direction, so just flip that sucker around and you'll be golden. The second version of the right-hand rule is a bit simpler to understand. This rule demonstrates the relationship between the direction of the wire's current and the direction of the magnetic field line. This is done by sticking your thumb in the direction of the current and curling your fingers. The direction your fingers curl in is the direction of the magnetic field line. If you need to know the direction of the current in the wire and you already know the direction of the magnetic field, then you can reverse this rule, hence the third right-hand rule, and let your thumb represent the magnetic field and your curling fingers represent the current.
Now, how do these actually affect things mathematically? Well, we don't want you to die while watching this video, so we will be doing things without calculus. Technically, because we are dealing with 3 dimensions, we need to use a cross product. But this is a bit too complicated for this level. The cross product is shown with the length of wire and the magnetic field right here. We will instead treat the magnetic force, which is shown by F, as perfectly perpendicular to both the current direction, which is right here, and the magnetic field. Similar to work, force is only applied through the perpendicular components, meaning that if it were not at a perfect 90 degrees, we would need to use the cross product. Now, once we've eliminated that, things become much simpler and we get this equation right here. In this equation, you can see that magnetic force is equal to current times length of wire times magnetic field with no cross products to worry about. Now, isn't that easy? Let's go ahead and try this example to see if you can calculate the force.
So this question asks, a wire of 75 centimeters long is carrying a current of 6 amps and is at right angles to a uniform magnetic field. The magnitude of the force acting on the wire is 0.6 newtons. What is the strength of the magnetic field? So in order to solve this problem, we need to get all of our units correct. We are sitting at 75 centimeters, we need to get to meters, meaning that it's 0.75 meters. And when you have the equation F equals ILB, B, which is your magnetic field, is equal to F over IL. So plug in your values. B is equal to 0.6 over 6 times 0.75, and B is equal to 0.13 T for magnet.
Now, because of the right-hand rule, humans have figured out how to use magnets to take pictures inside of us. It's pretty surprising, but the concept of the relationship between magnetic forces and currents in wires, as described by the second right-hand rule, can be applied to create machines that do MRI, or known as magnetic resonance imaging. So Trevor was talking about how he can use the second right-hand rule to modify it and create the third right-hand rule. The MRI machine applies that third right-hand rule, and basically what this right-hand rule says is that a coiled path of current, as shown right here, through a wire will create a straight path of magnetic field through the vertical axis of the superconducting magnet that the MRI uses. An MRI machine will apply the third right-hand rule using superconducting magnet. A superconducting magnet contains coiled wire, and after a current passes through that coiled wire, a magnetic field emerges, and the superconductivity of that wire strengthens the magnetic field that's present in the MRI machine. Now, how is this magnetic field used? We can actually use our water molecules in our body to have their alignments manipulated. This chart shows elements that are able to have tendency to align with the magnetic field that comes from the superconducting magnet, and it's known as elements that have magnetic moments. They have magnetic moments because they have a non-zero nuclear spin, meaning that there's an odd number of either or both protons and number of neutrons. In our chart, hydrogen makes roughly 60% of our body. That's because water makes up most of our body. This makes the hydrogen isotope, called protium, of the water molecules in our body the object of interest for the MRI. Therefore, the superconducting magnet, as shown as the main magnetic coil in this picture, will produce a magnetic field that the water molecules align with. Then the MRI machine will send radio wave pulses through a radio frequency coil with the correct frequency that creates resonance with the hydrogen protium. So right here, this is where the radio frequency and transmitter coils will be, so that they can send those pulses. And the frequency that creates resonance is called the Larmor frequency. The protons will experience disruptions with their alignment axis with the magnetic field, known as precessing. Precessing is when the protons are disrupted with their alignment axis. So as you see right here, the axis is when the magnetic field was applied, but now they'll be precessing around that axis because the radio waves have disrupted their alignment. The protons will recover their alignment by emitting radio frequency waves at the same frequency as the Larmor frequency. These waves will provide information to the machine about the time it takes to align with the field, the time it takes to realign with the field after precessing, and the density of these precessions. The first two types of information are called T1 and T2 relaxation times respectively. Therefore, T1 and T2 relaxation times and the density of proton activity is factored into creating MRI images. If you want different MRI slices, the MRI will use grading coils that will apply magnetic fields at different directions to have imaging of your body in the X, Y, and Z axis for three-dimension imaging. These grading coils, as shown as X magnetic coil, Y magnetic coil, and Z magnetic coil, are like the main magnetic coil because all four of them are electromagnets that have current going through a coiled wire in them to create straight paths of magnetic fields.